Today, I'm going to discuss albedo-shading decomposition by convolutional regression. These are the contents that I'm going to discuss. A new approach of intrinsic image decomposition has been discussed, which decomposes a single image into albedo and shading components. The direct intrinsics learns a convolutional neural network that produces output albedo and shading channels from an input RGB image. Direct intrinsics is a departure from the classical techniques for intrinsic image decomposition, which typically rely on physically motivated priors and graph-based reference algorithms. The large-scale synthetic ground truth of MPI Sintel data plays a key role in training direct intrinsics. Result: on both the synthetic images of Sintel and the real images of the classic MIT Intrinsic image dataset are demonstrated. On Sintel, direct intrinsics using only RGB output outperforms all the prior work, including methods that rely on the RGB and depth input. Direct intrinsics also generalizes across modalities. It produces quite reasonable decompositions on the real images of the MIT dataset. The results indicate that the marriage of CNNs with synthetic training data may be powerful for tackling classic problems in computer vision. The data availability roadblock is circumvented by training on purely synthetic images and testing on both real and synthetic images. The MPI Sintel dataset produces photorealistic rendered images and corresponding albedo shading ground truth derived from the underlying 3D models and art assets. These were first used as training data by Chen and Colton for deriving a more accurate physics-based intrinsics model. Now, what is direct intrinsics? We construct a CNN that, acting across an input image, directly predicts the decomposition into albedo and shading images. It essentially encodes nonlinear convolutional kernels for the output patches, indicated by the green boxes, from a much larger receptive field in the input image, the cyan box. Systems motivated by physical priors are usually formulated as optimization routines solving for a point-wise decomposition, and also fits with priors imposed over an extended spatial domain. The direct intrinsics approach is purely data-driven and learns a convolutional regression which maps a color image input to its corresponding albedo and shading outputs. It is instantiated in the form of a multi-scale FCNN. Key to enabling our direct intrinsic approach is availability of a large-scale dataset with example ground truth albedo shading decompositions. Unfortunately, collecting such ground data for real images is a challenging task, as it requires full control over the lighting environment in which images are acquired. This is possible in a laboratory setup, but difficult for more realistic scenes. Coming on to the architectural structure. There are two architectural variants that are explored for implementing the direct intrinsics network shown in the figure. The left image is motivated by the multi-scale architecture used by Eigen and Fergus for predicting depth from the RGB. A similar network structure is used for direct prediction of albedo and shading from RGB and termed as multi-scale CNN regression or MSCR. On the right hand side, we have a recent work which shows value in directly connecting intermediate layers to the output. A version of such connections is used in the scale 1 subnetwork adopting the hypercolumn terminology. The subnetwork of scale 2 is identical to that on the left, where M is the input size factor. Intrinsic decomposition requires access to all the precise details of an image patch as well as an overall gist of the entire scene. The multi-scale model of Eigen and Fergus for predicting scene depth has these ingredients, and our network architecture is based on it. They first extract global contextual information in a coarse subnetwork and then use that subnetwork output as an additional input to the finer scale network. In MSCR architecture, instead of a fully connected layers in scale 1, a 1x1 convolutional layer is used following the upsampling layer. This choice enables our model to run on arbitrary sized images in a fully convolutional fashion. For nonlinear activation, we use parametric rectified linear units or p-ReLUs. With p-ReLUs, a negative slope for each activation map channel appears as a learnable parameter. The network has two outputs, albedo and shading, which it predicts simultaneously. We optionally use deconvolution to learn to upsample the scale to output to the resolution of the original image. Without deconvolution, we upsample an RGB output. In addition to these basic changes, we explore a variant of our model that connects multiple layers of scale 1 subnetwork directly to the subnetwork's output. The reasoning follows that the objective of directly capturing a representation of the input at multiple levels of abstraction. We adopt the hypercolumn terminology to designate this modification to MSCR. The remaining architectural details are as follows. For convolutional layers 1 through 5 in the scale 1 net, we take the common AlexNet design. Following those, we upsample the feature map to a quarter of the original image size and then feed it to a 1+1 convolutional layer with a 64-dimensional output. The scale 2 consists of 4 convolutional layers for feature extraction followed by albedo and shading prediction. The first of these layers has 9x9 filters and 96 output maps. Subsequently, we concatenate outputs of the scale 1 subnetwork and feed the results into the remaining convolution and prediction layers, all of which use 5x5 filters. The optional learned deconvolutional layer uses 8x8 filters with a stride 4. Whether using deconvolution or simply upsampling, we evaluate our output on the grid of the same spatial resolution as the original image. For training data, we follow Chain and Colton and use the clean pass images of MPI Sintel Dataset instead of their final images, which are the result of additional computer graphics tricks which distract from our application. This eliminates effects such as depth of field, motion blur, and fog. Ground truth shading images are generated by rendering the scene with all elements assigned a constant gray albedo. Some images contain defect pixels due to software rendering issues. However, limited variation within the Sintel dataset is a concern for data-driven learning. Hence, we use the defective images as well in training by masking out the defective pixels by actually ignoring their contribution to the training error. To demonstrate adaptability of the model to the real-world images, we use the MIT Intrinsic image dataset. Images in the dataset are acquired with special apparatus, yielding ground truth reflectance and shading components for real-world objects. Here, reflectance is synonymous to albedo. Due to the limited scalability of the collection method, the MIT dataset contains only 20 different objects, with each object having 11 images from different light sources. Only one image of 11 has shading ground truth. We generate each of 10 shading images S from a corresponding original image I and reflectance image A by finite element-wise division. For models trained on MIT, we denote inclusion of these additional generated examples in training by appending the designation GenMit to the model name. Some images in the MIT dataset do not exactly follow I is equal to alpha AS relation, but including these generated shadings will still improve the overall performance. Even after generating shading images, the size of MIT dataset is still small enough to be problematic for data-driven approaches. While we can simply train on Sintel and train on MIT, we observed some differences in dataset characteristics. Specifically, the rendering procedure generating Sintel ground truth produces output that does not satisfy I is equal to alpha AS. In order to shift the Sintel training into a domain more representative of real images, we resynthesize ground truth I from the ground truth A and S. In experiments, we denote this variant by resynth Sintel and find benefit from training with it when testing on MIT. The images are mirrored and cropped to generate additional training datasets. Since the intensity of our ground truth albedo and shading is not absolute, imposing standard regression loss, the L2 error, does not work. Hence, to learn the error theta, we use the scale invariant L2 loss described in the equation. Let y star be the ground truth image in log space of either the albedo or shading, and y be a prediction map by denoting small y is equal to capital Y star into minus y as the difference, the scale invariant L2 loss is as shown in the equation, where I and j are image coordinates and c is the channel index and n is the number of evaluated pixels. Lambda is the coefficient for balancing the scale invariant term. It is least square loss when lambda is equal to 0, scale invariant loss when lambda is equal to 1, and an average of the two when lambda is equal to 0.5. In this, we have selected lambda is equal to 0.5 for training on MIT or Sintel separately, as it has been found to produce good absolute scale predictions while slightly improving qualitative output. We select lambda is equal to 1 for training on MIT and Sintel jointly, as the intensity scales from the two datasets differ and the generated images no longer preserve the original intensity scale. The loss function of our MSCR model is the gradient L2 loss. We also consider training with loss that favors recovery of piecewise constant output. To do so, we use the gradient loss, which is an L2 error loss between the gradient of prediction and that of ground truth, by letting del I and del j be the derivative in the I and jth dimensions respectively of an image. Shading cannot be assumed piecewise constant. We do not use gradient loss for it. Our objective with gradient loss is shown. We denote as MSCR plus GR the version of our model using it. Though large compared to other datasets for intrinsic image decomposition, MPI Sintel with 890 examples is still small compared to the large-scale datasets for image classification, on which deep networks have been a success. We find it necessary to add additional regularization during training and employ dropout with probability of 0.5 for all convolutional layers except con1 through con5 in the scale 1. We implement our algorithms in the CAFE framework. We use SGD with random initialization and momentum of 0.9 to optimize our networks. Learning rates for each layer are turned by hand to get reasonable convergence. We train networks with a batch size of 32 for 8,000 to 50,000 mini batch iterations. Depending on the convergence speed and dataset, we randomly crop images at a scale of 416 x 416 pixels and mirror them horizontally. For additional data augmentation, we also randomly rotate images in the range of -15 to 15 degrees and zoom it by a random factor in the range of 0.8 to 1.2. Due to the architecture of our scale 1 subnetwork, our CNN may take as input any image whose width and height are each multiple of 32 pixels. For testing, we pack the images to fit this requirement and then crop the output map to the original input size. In total, we use 890 images in the Sintel Albedo-shading dataset from 18 scenes with 50 frames each. We use two-fold cross-validation, that is training on half of the images and testing on the remaining images, to obtain our test results on all the 890 images. Our training and testing split is a scene split, placing an entire scene either completely in training or completely in testing. Coming on to the empirical evaluation, we have adopted the same three error measures as MSE, the mean squared error between albedo shading results and the ground truth. We use scale invariant measures when benchmarking intrinsic results. The absolute brightness of each image is adjusted to minimize the error. LMSE is the local mean squared error, which is the average of scale invariant MSE errors computed on overlapping square windows of size 10% of the image along its larger dimension. DSSIM is the dissimilarity version of the structure similarity index. The SSIM characterizes image similarity as perceived by human observers. It combines error from independent aspects of luminance, contrast, and structure, which are captured by mean, variance, and covariance of patches. Coming on to results. The top panel of table shows that evaluated on Chain and Colton test set, our MSCR dropout and GL model significantly outperforms all competing methods according to MSE and LMSE. It is also overall better according to DSSIM than the current state-of-the-art method of Chain and Colton. While our albedo DSSIM is larger, our shading DSSIM is smaller. Chen and Colton's method utilizes depth information and is also trained on the DSSIM measure directly, whereas ours is based on the color image alone and is not trained to optimize the DSSIM score. The bottom panel of table 1 is more indicative of an algorithm's out of sample generalization performance. The test scenes have not been seen during the training. These results shows that the out of sample errors in the scene split case are generally larger than in sample errors in the image split case. While hypercolumn has negligible effect, each tweak with dropout, gradient loss, learned deconvolution, and data augmentations improve performance. Training on Sintel and MIT together provides a small improvement when testing on Sintel. This figure displays a side-by-side comparison with 3 other approaches. An important distinction is that our results are based on RGB alone, while the other approaches require both RGB and depth input. Across a diversity of scenes, any of these 3 RGB plus depth approaches could break down in one of the scenes on either albedo or shading. Example, the Lee et al.'s method on the bamboo scene, the Barron's method on the dragon scene, the Chen and Colton's method on the old man scene. The quality of our results is even across scenes and remains consistent with the albedo and shading ground truth. Coming on to the next slide. Comparing on MPI Sintel, we compare our intrinsic image decomposition with those of Lee et al., Barron et al., and Chen Colton. Our algorithm is unique in using only RGB and not depth input channels, yet it generates decomposition superior to those of the other algorithms, which all rely on full RGB plus depth input. The table 2 shows that our model graciously adapts to real images. Trained on MIT alone, it produces reasonable results, naively adding Sintel data to training hurts performance, but mixing our resynthesized version of Sintel into training results in noticeable improvements to albedo estimation when testing on MIT. The behavior of ablated system variance on MIT mirrors our findings on Sintel. On MIT, the learned deconvolutional layer is especially important. Output in the figure clearly exhibits clear visual degradation upon its removal. The figure illustrates a trade-off when using resynthesized Sintel training data, as there is an overall benefit but a Sintel specific shading prior the bluish tint leaks in. Adaptability to real images. Our base system, the MSCR plus dropout plus decon plus data augmentation plus GenMet, produces quite reasonable results when trained on the MIT Intrinsic dataset. Without learned deconvolution, both albedo and shading quality suffer noticeably. Including resynthesized Sintel data during training improves albedo prediction, but biases shading towards Sintel specific lighting conditions. Coming to the conclusion, we proposed direct intrinsics, a new intrinsic image decomposition approach that is not based on the physics of image formation or the statistics of shading and albedo priors, but learns the dual association between the image and the albedo plus shading components directly from training data. We developed a 2-level feed-forward CNN architecture based on a successful previous model for RGB to depth prediction, where the coarse level architecture predicts the global context and the finer network uses the output of the coarse network to predict the finer resolution result. Combined with well-designed loss function, data augmentation, dropout, and deconvolution, we demonstrate that direct intrinsics outperforms the state-of-the-art methods that rely not only on more complex priors and graph-based inference, but also on additional input of scene depth. Our data-driven learning approach is more flexible, generalizable, and easier to model. It only needs training data, requires no hand-designed features or representation, and can adapt to unrealistic illuminations and complex albedo, shape, and lighting patterns. Our model works with both synthetic and real images and can further improve on real images when augmenting training with synthetic examples. These were the references used while framing the presentation. Thank you.